Okay, good afternoon, everyone, and welcome to the SimEA project seminar series. So the SimEA project seminar series aims at promoting and disseminating scientific knowledge, particularly in the field of computational science and engineering. Today we have two speakers who are in the SimEA project, two PhD students, who have recently joined the SimEA research team, namely Nikolaos Patsalidis and Eleftherios Christofi, who will present their MSc research projects and give an overview of the research that they will be conducting during their PhD at the Cyprus Institute and under the SimEA project. I would like to begin by introducing our first speaker, who is Eleftherios Christofi. Eleftherios received his Bachelor of Science degree in Mathematics from the University of Crete, and thereafter completed his Master's degree in Applied and Computational Mathematics, working in the machine learning field. As a PhD student, he will work on the development of multi-scale simulation approaches for complex molecular systems via hybrid physics-based data-driven methods. Eleftherios, I will now pass over to you.
Okay. Hello, my name is Christophe Eleftherios. I'm an applied mathematician, and I enjoyed the SimEA project as a PhD student 12 months ago. Today, I'm going to present you my master's degree thesis. The title of my thesis is Optimization Algorithm in Machine Learning. First, we can see some applications of deep learning, like for example in medicine, where with the help of image classification, we are able to detect abnormalities in an X-ray. Moreover, object detection has applications in the autonomous driving field from companies like Tesla. We will start with mathematical formulation of the problem. Here we see the general form of a deep neural network, where each circle denotes a neuron and a column of neurons represent a layer. The first layer is the input layer, which supplies the information into the system. Then we have the hidden layers, which execute the calculations and pass the results to the output layer. And last, we have the output layer, which presents us the information identified by the network. On the right, we have a diagram which illustrates the calculation of a single neuron output. Each neuron has its own weight. We compute the weighted sum and add a bias. Then we pass this sum through an activation function to get the output. Next, we generalize our relation for the single layer's output, where A capital L contains each neuron's output of the current layer, WL contains each neuron's weight of the previous layer, and BL contains each neuron's bias of the current layer. For the activation function, we choose a sigmoid activation function. It takes values between 1, we say that the neuron is active, and 0, we say that the neuron is inactive. We can modify the behavior of the function with this equation, where W controls the steepness of the function and B controls the displacement in X direction. In order to measure the error between the values predicted by the model and the actual value, we need a cost function. We choose a quadratic cost function, which measures the distance between the output and the target output. The process of the cost function minimization is called training process. Gradient descent is the most popular method to do that. As we can see, it follows a negative slope. Here's the update rule, where eta is the learning rate, which determines the size of our steps towards the negative slope. Backpropagation provides us with a numerical method to compute the partial derivatives of the cost function with respect to any parameter. Here we have the four fundamental equations of backpropagation. Thus, by doing a forward pass in the network, we get the output, which is the A capital L. Hence, we can calculate delta capital L, and then with a backward pass, we compute the rest of the deltas, which can give us the partial derivatives. So here we have a simple implementation of deep learning. The graph represents 10 points in the two-dimensional space, which are divided into two groups. Group A is denoted by red triangles and Group B by green circles. Here we have the target outputs for each group. To implement this example, we choose this network, which have three layers. The input layer have two neurons because of the nature of our data set. The output layer also have two neurons because our target outputs lives in the two-dimensional space. With a forward pass through the network, we calculate the outputs, which is the A3. And then with a backward pass, we calculate the deltas, which give us the gradient of the cost function. Then graph illustrates the behavior of the cost function after a number of gradient descent iterations, which shows a decreasing trend. We continue with an overview of the gradient descent algorithms. Gradient descent has three main variants: batch, stochastic, and mini-batch gradient descent. These algorithms differ on the amount of data they use to compute the gradient of the cost function. Batch gradient descent uses the entire training set to perform an update. Thus, is computationally efficient and has stable convergence, but it has slower learning and can be easily get trapped in local minimums. On the other hand, stochastic gradient descent performs an update for each sample. Hence, because of the oscillations, it can escape from non-optimal local minimums, and we have faster learning, but it's computationally expensive and cannot remain at the global minimum. Mini-batch gradient descent is a mixture of the previous two, so it performs an update for each mini-batch of size m. Therefore, it combines the advantages of these algorithms, but on the other hand, we introduce a new hyperparameter m, which is hard to optimize. Also, the algorithm can get trapped in local minimums. These algorithms face some challenges. Choosing the proper learning rate could be difficult. Learning rate that is too small leads to slow convergence, while a learning rate that is too large can cause the cost function to oscillate around the minimum or even to diverge. Moreover, the same learning rate applies to all parameter updates. If our data is sparse and our features have very different frequencies, we might not want to update all of them to the same extent. Furthermore, for non-convex error functions, the algorithm can get trapped in their numerous suboptimal local minima or in their Sartori points. The following algorithms deal with those challenges. As we can see, gradient descent has trouble navigating ravines, which are areas where the surface curves much more steeply in one dimension than another, which are common around local minimum. It oscillates across the slopes of the ravine while making small progress towards the local optimum. Momentum helps accelerate gradient descent in the right direction and decrease oscillations. It does this by adding a fraction gamma of the output vector of the past time step to the current update vector. This picture illustrates how momentum works. Decreases updates for dimensions where the gradients points in the same directions, and reduces updates for dimensions where the gradients change directions. NAG is an improved version of momentum because it uses this look-ahead term to compute the gradient. NAG first makes a big jump in the direction of the previous accumulated gradient, and then measure the gradient where you end up and make a correction. Next, we have Adangrand, which adapts the learning rate to each individual parameter j at every time step I, but it has a major disadvantage that it accumulates the squared gradients in the denominator. Since every added term is positive, the accumulated sum keeps growing with the training. Thus, it causes learning rate to shrink, and the algorithm is no longer able to acquire additional knowledge. To solve that problem, RMSProb expresses the sum of the past square gradients as a decaying average of these gradients. Here we set gamma to a similar value as the momentum term, around 0.9. Ada delta eliminates the learning rate term from the update rule by using the root mean squared error of parameter updates until the previous time step. Next, we have Adam, which is a combination of momentum and RMSProb, because MI and VI are initialized as vectors of zeros. They are biased towards zero. Thus, we correct this bias by computing these bias-corrected terms, where beta 1 and beta 2 are positive constants. Adamax is a variant of Adam derived from the infinity norm. We generalized the VI term like this. By calculating the limit, we get UI, which gives us the update rule. Finally, we have NADAM, which is a combination of NAG and ADAM. Therefore, choose this combination because, as we saw before, NAG is better than momentum. On the left, we see a table of gradient descent algorithms, the components they act upon. Momentum and NAG act upon the gradient, ATA and grant, RMS probe, and ATA delta act upon the learning rate, while ATAM, ATAMax, and ATAM act upon both. On the right, we see some proposed default hyperparameter values for each gradient descent algorithms. And usually we change only the value of eta. So now we will compare these algorithms by using the example we saw at the beginning. The first neural network has 2 hidden layers with 2 and 3 neurons each, which give us a total of 23 parameters to optimize. Here we see some numerical results. We have 2 groups of tables. In the first group, we calculate the time and the number of iterations needed to reach this tolerance. The second group computes accuracy after 500,000 iterations. As we can see, RMS probe is the fastest algorithm that will reach the desired tolerance in all 3 variants, while ATAMax managed to score the highest accuracy. On the second neural network, we have one hidden layer with 6 neurons. Thus, we have 32 parameters to optimize. As before, RMS probe is the first algorithm to reach the desired accuracy, while the adaptive gradient descent algorithms take the last spots. Again, ATAMax reached the highest accuracy after the given iterations. Finally, on the third neural network, we have a hidden layer with 12 neurons, which has a total of 62 parameters to optimize. Same as before, RMS probe scored the best time, while ATAMax reached the highest accuracy, but it experienced a significant drop compared to the previous networks. The given animation shows the behavior of the algorithms at the sample point. Stochastic gradient descent momentum and NAG find it difficult to break symmetry, while ATA and grant RMS probe that delta find immediately the right path. To conclude, for this data set, the numerical results indicate that the algorithms perform better in the first neural network, and thus the number of the parameters is not proportional with the performance of the algorithms. And finally, the adaptive learning rate methods outperform the adaptive gradient ones. And now, during my thesis, we proposed to apply machine learning methods to parameterize coarse-grained models for complex molecular systems. We are going to examine various multidimensional functional basis sets, and we will apply these methods for realistic models to materials of a scientific and technological importance, such as simple fluids, polymers, and biomolecular systems.
Great. Thank you, Eleftherios. We would now like to invite any of the attendees to ask questions.
Vangelis, he need to make a question. Vangelis.
Okay. So,
There we go.
everyone, can you hear me now?
Yes, we can hear you.
Okay, thank you very much, sir. Yeah, so I'm just wondering, Lefteris, okay, so it was very nice, all this detailed, let's say, examination of the performance of the algorithm for this specific data set. Do you think that you will have, let's say, the same qualitatively or quantitatively results if you examine a much different data set, for example, a much larger data set, or a data set involving data from different fields or from different data sets?
Okay. Actually, in order to do that, of course, you need to try these algorithms in a bigger or several data sets in order to get more reliable results. Actually, these results on this small data set shows a path on how they may actually perform on a larger data set. So I guess I can answer that.
Okay, so it is something that could be investigated.
Yes, yes, of course.
And if I may ask one more, so concerning now the structure of the network, if I'm not wrong, you examined primarily these two different networks.
Three different networks.
Can you please discuss a little bit that more, how the structure of the network affect, let's say, the convergence of the algorithm in this specific data set? Okay. I mean, is it better to go to increase, let's say, the width or the depth of the neural net?
The numerical results indicate that if you increase the number of the layers, it improves your results. But if you improve the number of neurons on a specific layer, you get more parameters to optimize, but you did not get a proportional good result.
So if we have, let's say, a constant, under the constant overall number of nodes, can you predict, let's say, the best structure of the network?
I cannot predict the best structure of the network, but
at least among the ones that you have checked, or
yeah, as we saw here, this neural network performs better than the other ones, which have, as we can see, more neurons in the hidden layer.
Mm-hmm.
Any other questions?
We don't have any other questions.
Okay, great. Well then, we will move on to the second presentation now by Nikolaos Patsalidis. Nikolaos studied mechanical engineering at the National Technical University of Athens, where he graduated with an integrated master's specializing in air and ground transport vehicles. And in his thesis, he developed a multi-objective optimization algorithm and applied it in aerodynamic applications, where he developed an innovative gradient-based method to solve up to 3 objective optimization problems. So after giving an overview of his MSc research experience, he will then present his current research pertaining to multi-scale modeling and machine learning algorithms for predicting the mechanical problems of complex materials. Nikolaos, I will now pass over to you.
Hello, good afternoon, everyone. Today I'm going to present you my master thesis project, which is about development of an algorithm and software for computing Pareto fronts with a gradient-based method with application in aerodynamics. And I will also talk a bit about my current research project as a new PhD student in SimEA, which is about multi-scale modeling and machine learning algorithms for predicting the mechanical properties of complex materials. So the main thesis objectives for my PhD projects is to predict the mechanical properties of complex molecular systems through multi-scale computational approaches and machine learning algorithms, to derive atomistic and mesoscopic models for specific homogeneous and multi-phase liquid and solid systems by analyzing large datasets for more detailed simulations, such that density functional theory calculations, and solve optimization problems over a large and high-dimensional space in order to derive those models. We will also explore applying machine learning methods to parameterize models for complex liquid and solid interfacial systems. And finally, then derived algorithms and codes will be optimized for hybrid CPU and GPU architectures. So about my master thesis project, it was developed within the parallel CFD and optimization unit of School and Mechanical Engineering at the National University of Athens, and under the supervision of Professor Kyriakos Giannakopoulou. The algorithm is an extension, and the project is an extension of two older thesis projects of Mariou Kapsi and Marianna Scaruzu. But because of the major changes, I programmed a new algorithm in C++. This algorithm calculates Pareto points successively, and for each Pareto point calculation, I used an iterative method. At each iteration, the algorithm uses external software to calculate the objective values and the objective first derivatives. And this external software in this thesis, it is called PUMA, which is a CFD solver developed in the parallel CFD and optimization unit, which also includes an adjoint solver that can calculate the objective first derivatives with the use of the continuous adjoint method, which has the advantage that the computational cost for the calculation of the derivatives is independent to the design space size. To evaluate the performance of these algorithms, I used a software called EASY, which is an evolutionary algorithm, also developed in parallel CFD and optimization unit. And the reason is that generally these algorithms are capable of computing global solutions if they run enough time. The drawback of such algorithms is that the computational cost is proportional to the design space size, and that it is what I try to do to make a fast algorithm that can calculate Pareto fronts faster. So the main thesis objectives were to calculate three-dimensional Pareto fronts, in contradiction with the previous thesis project that only two-dimensional Pareto fronts could be calculated, to also add some complexity to the optimization problems that could be solved by adding to the problems maybe equality constraints or inequality constraints, to lower the overall computational cost, and finally to evaluate the algorithm in aerodynamic applications by comparing the results in the computational cost with the cost of an evolutionary algorithm. The basic idea of this algorithm is to constrain all objectives apart from one that becomes the target to be minimized. In other words, we minimize, let's say, the objective F1, and we set all the other objectives to have a certain value F hat. In this way, we can successively solve this single objective constraint problem, and by varying these values of F hat to get new Pareto points. I would also like to mention that this algorithm is a prediction correction algorithm, and let me elaborate a bit more in that, which means that let's say that we have an initial Pareto point in that simple two-objective example that we calculate from single objective optimization of the first objective. Then with a first order mathematical scheme, we can approximate a neighbor solution with the value of F2 hat. Because this is only an approximation, then we use an iterative method called sequential quadratic programming to calculate the exact values, the exact Pareto point. This procedure can be then continued and successively calculate Pareto points. And to understand the mathematical implementation of that prediction step, let's assume that we only have two objectives. And then to be on the Pareto front, which the prediction step is valid, because if we are not on the Pareto front, this prediction step is not valid. We need to satisfy the Karush-Kuhn-Tucker conditions, which are just that the gradient of this Lagrangian function is equal to 0, but also the constraints are satisfied. By using the implicit function theorem, we can derive the below equation, and which is nothing but this system of equations, where we can see that in the left-hand side, we have the gradient, the first derivatives of the objectives, but also the second derivatives of this Lagrangian function. We calculate the first derivatives with our external software, and these second derivatives we approximate with a quasi-Newton method called BFGS to avoid the large computational cost. If we solve then this linear problem, we can get these derivatives of the design variables and the Lagrange multiplier over the F2 hat value, and we can use them in a first order Taylor expansion to approximate a new Pareto point in the design space. If you want to generalize this, we need to add in the Lagrangian more objectives, equality constraints, and the active inequality constraints. By active inequality constraints, we mean the inequality constraints that satisfy the equality on the Pareto front. Then we get this mathematical scheme, which is the same as the previous one. Just we add more column vectors of the gradient of the other constraints to the system, and we use the Taylor expansion to approximate a new Pareto point. On the other hand, for the correction step, we use the SQP solver, which, if we observe, it has the same left-hand side as the prediction step, and that is an advantage because we can calculate in each of these correction step iteration a new Hessian matrix with an approximation method, a quasi-Newton method, and then use it in the prediction step for the calculation of the next point. We see that in the correction step, we calculate corrections for our Lagrange multipliers and design variables. And if we want to summarize the algorithm's flow, we will need to say that we first calculate a point on the Pareto front. For example, with single objective optimization, we vary f hat, we perform the prediction step, and then in the correction step, we calculate the objective values, and we also calculate the first derivatives of the objectives and the constraints. This is done by our external software, and that's why we have the most of the computational cost in this step. We measure the total computational cost in equivalent flow solutions, and this step, each time we call this software, it has about 2 equivalent flow solutions, because we need to solve the primal CFD problem in order to calculate, let's say, the objectives, which could be the drag coefficient or the lift coefficient. And we also need to solve the adjoint problem in order to calculate the first derivatives, which has about 1 equivalent flow solution computational cost. So we have in total of 2. To continue this algorithm, we renew the Hessian matrix with the BFGS method. We estimate the inequality constraints in order to include them in the linear system of the SQB solver. And then after we solve this problem, then we can correct our design variables in Lagrange multiplier, and after a few steps, we converge to the Pareto point, and we can calculate then the next point by following the same procedure until we successively calculate all the points we want. Now, what I haven't answered is how do we vary these f hat values in order to always calculate non-dominated solutions, but also to demand a value for that objectives that it is actually possible. Let's say for the 2 objective problem, we perform single objective optimization for both targets. Then we will calculate the edges of this of the Pareto front, and then we can discretize the internal field for the f2 hat values, and then we will be sure that if we set these values to the second objective as constraint, we will be sure that we will calculate a non-dominated solution, thus Pareto points. We can then calculate these points following a path, let's say starting from the above point, and by the prediction correction algorithm to successively compute all these points. On the other hand, for the calculation of the 3 objective Pareto fronts, we need to calculate these pair values for f2 hat and f3 hat, and we perform single objective optimization for all the targets, and we'll get some points like this if we project them in this f2, f3 space. And then we calculate 3 two-dimensional Pareto fronts, f1, f2, f1, f3, and f2, f3. And if we project them in this space, then we will get a curve like this. Then we can realize that this is actually the boundary, this curve is actually the boundary of the 3-dimensional Pareto front. And we can, if the Pareto front is continuous, then we can discretize this field and get pair values for f2 hat and f3 hat. And then again, with the prediction correction algorithm, by following a path, for example, like this, to calculate all the internal points we want on the Pareto front. To see some applications, I applied these algorithms in aerodynamic shape optimization of an airfoil in 2 slightly different flow conditions. As optimization objectives, I used the minimization of the drag coefficient, the maximization of the lift coefficient, and the maximization of the area of the airfoil. For example, for the wing of an aeroplane, these objectives correspond to less fuel consumption. We can carry more weight if we maximize the lift coefficient, and maximization of the area of the airfoil corresponds to the maximization of the volume of the wing, which is used generally to carry fuel. To see the domain, we can see here the domain of the CFD problem and the two-dimensional mesh, but also we can see that the airfoil, the shape of the airfoil is parameterized with these Bezier control points, these square points that define the shape of the airfoil. In these problems that I solved, I vary these red squares and these blue squares in the y direction and so that the y coordinates of these points are actually the design variables, because if we change them, then the shape will change, and that's why we have a total design space size of 8. So the first problem that was solved was a two-objective problem with bounded design variables. To bound certain design variables add some complexity to the problem, because there are a lot of inequality constraints. The targets were to minimize the drag coefficient and simultaneously to maximize the lift coefficient. We can see on the right up of the slide the Pareto front, the Pareto points actually with the blue squares, and the prediction points, we can see that they are very close to the correction points. And these label points correspond to these optimal shapes of the airfoil, where you can see in this unscaled figure and in a scaled one below. And also to the bottom right of the slide, you can see the comparison with the evolutionary algorithms. The red cycle points correspond to the Pareto points that were calculated with the evolutionary algorithm. And we can see that with this gradient-based method, we can actually get this Pareto front with a lot less computational cost in general. And if we want to add another constraint, another objective to the problem, then we add the maximization of the area of the airfoil. And with that method, we need to also compute the Pareto F1 and F3, the Pareto F2 and F3. And if we project these Pareto fronts, then we will get this curve in this F2, F3 space, and we can discretize this area in order to get pair values F2 hat and F3 hat. And then by calculating successively these points following this path, we calculate the three-dimensional Pareto front. To see some results, we can see the three-dimensional Pareto front, but also its projection to the two-dimensional spaces, but also some optimal shapes that the airfoil takes in some points. And we also compared the results with that of the evolutionary algorithms. Its points, the points of the evolutionary algorithm correspond to these green cycles, and we can see that the computational cost is about the same, but we need to consider that this is a problem with a very small design space size, and I think it's a good assumption that to make that if the design space was bigger, that we will actually have a gain in computational cost. We can also verify that these Pareto fronts are actually the same, with the difference that with this gradient-based method, we can actually calculate better the boundary of this Pareto front, which is essentially all the essence in that method. So now I present you a solved three-dimensional problem with the same objectives, but I also added inequality constraints that set the third objective a minimum and a maximum value, and in some slightly different flow conditions. We calculate the Pareto front F1 and F2, Pareto front F1 and F3, and if we project these Paretos on the F2, F3 space, we will see that to close this curve, we only need to draw this line which corresponds to this second inequality constraint. If we discretize this field and get pair values for F2 hat and F3 hat, then we can calculate the internal points of the Pareto front, but this time we calculate these 15 points following this different path than these 6 points. And this is done because those points were calculated in different processors than this second path points. And this is just to show that different Pareto points can be calculated in parallel processors, and that is possible. To see the results of this problem, we can see the three-dimensional Pareto front and its projection to the three two-dimensional spaces, but also the optimal values, the optimal shapes of the airfoil, which correspond to these points. Again, we compare the results with that of an evolutionary algorithm, and we see that again these Pareto fronts are similar. If you observed, all these problems had computational cost with the presented algorithm. The computational cost per point was actually about 10 and constant, and that's something that was observed during all those problems. Now, finally, I solved the two-objective problem with an equality constraint, just to show that it's possible. Now the third objective is actually set as an equality constraint. I mean, the area of the airfoil is set to be constant. And we see again that the Pareto front was computed in a low computational cost, total of 77 equivalent flow solutions, and we see the shapes that the airfoil takes in these labeled points. Again, the prediction points were quite a good approximation for these Pareto points. And to conclude, now we see that with this gradient method, three-dimensional Pareto fronts can be done in an effective way. Problems with equality and inequality constraints can be solved, and that there is a different Pareto points to be calculated in parallel, but also the computational cost per Pareto point is approximately constant. So what's left to be done is that we can calculate the variation of F2 hat and F3 hat in such a way that the Pareto front is dense enough for our needs, but with the less points. Also to program the code in order for difficult points to be calculated in parallel automatically, and to extend the logic to calculate Pareto fronts with bigger objective space dimensions. Thank you for your attention. If you have any questions. Yeah.
Thank you, Nikolaos. As you said, we will now open for any questions. Vangelis, did you have a question?
Thank you, Kathy. Yeah. So just wondering, Nicolas, it was very interesting, the presentation. So just two, let's say, short questions. The first is related with what you mentioned as future plans. So what is the computational cost when you have to deal with a much, let's say, larger optimization problem. So if I understand well, the problems that we checked are 2D and 3D in principle. And then the second is related with the form of the CD, CL, and D that we presented, which is not clear to me. What are the form of these functions? Are there linear functions, non-linear? Do we have any limitations on the type of functions that can be used or not?
I'm not sure I understand the second question. For the predictions, the mathematical implementation.
No, what type is the functions, the CD and CL and D? Are there specific?
No, you mean the drag coefficient and the lift coefficient that were set as objectives.
Mm-hmm.
Yeah, they are highly non-linear because in order to calculate them, we need to solve all the CFD problem, and that's why you have a big computational cost.
So this is coupled with that. That's what you didn't present actually. So it's coupled with the CFD.
Yes.
So it's the output of the CFD actually.
Yes,
but
and
it's not a vector. This is just a scalar quantity.
Yes, it's a scalar quantity that we want to minimize.
Okay. So then you have a problem which is either 2D or 3D. So if we have several more, let's say, or if we have minimization over a high dimensional space.
I can think two problems for that. The first problem is that, let me go, okay, here. In order to compute with this method highly dimensional spaces, we need to compute, for example, if we had 4 objectives, then we need to compute 4 single objective optimization points. Then we need to compute all the pairs. We can get, I think it's 7 to the Paretos, and then 3 dimensional Pareto fronts in order to make somehow this similar boundary, in order to have these values that we set as constraints, because then we will not know how to what values to set these constraints. We can set some values that we guess that that we could find optimal solutions, but we will not be sure. And also, if we add more objectives to the problem, I think for a Pareto front to be dense enough, I mean, to find the optimal solutions and have a dense enough Pareto, we will need to calculate more points in general. For example, in this 2-dimensional point, we only calculate 7 points, and we maybe think that it is dense enough. But for this 3-dimensional, we calculated in my first problem, I calculated for this 2-dimensional problem 9 points, and for this for that problem I think it's 35 points, and that's why the computational cost is bigger. Mm-hmm. And one final point that we should make is that because it is a gradient-based algorithm, and every time we need to compute the gradients of the objectives or the constraints, we need to have an efficient method that calculates the gradients. For example, if in CFD, if we use the finite differences to calculate those derivatives, then we will also have to solve the problem, the primal CFD problem another 2 times, which is very computational costly. We just use a smart, let's say, method which is called continuous adjoint method to calculate the derivatives. This method I didn't develop it; it was already developed within the unit.
Yeah, so this is a numerical method in order to calculate the derivatives, if I understand well, right?
The continuous adjoint method.
Yeah, this is standard method. It's a standard thing.
Yeah, yes, it has a lot of for each specific problem you have. Let's say you have to develop it mathematically. That's its drawback. But then you can, I think actually if you solve the primal CFD problem, that is what is called, you can calculate then the derivatives analytically with the exact derivatives. So.
Okay, thank you, Nicholas.
Thank you.
Are there any other questions?
We don't have any other questions.
All right, well then in closing, I would like to thank Eleftherios and Nicolas for their presentations. And I would like to thank you all for joining us for the final seminar of the year. And we look forward to seeing you all in the new year. Goodbye, everyone.
Thank you. Bye-bye.
Thank you. Bye.